The new age of illumination created an accelerated demand for the fuel that kept America's oil lamps burning. The collection process at naturally occurring oil seeps would clearly not keep up with the growing thirst for more and more oil. Despite numerous setbacks and technical complexities, Edwin L. Drake and his driller Billy Smith, who were convinced that the underground pools that fed the seeps could be tapped, struck oil with the world's first commercial well. On August 27, 1859, in Titusville, Pennsylvania, what had been derided as Drake's Folly began pumping nearly 20 barrels a day. This was an extraordinary amount of production compared to the meager results available from seep collection. It was the start of the Pennsylvania oil rush. 40 days later, on October 6th of the same year, Billy Smith was conducting an inspection of vat levels with an open lamp and created the first commercial oil well explosion and fire. The gases and vapors that collected in the vat ignited and the oil burned. In addition to the vats, the derrick and Smith's adjacent home were consumed in the blaze. Even with the sophistication of current engineering techniques and the exceptional diligence employed in the design and operation of drilling systems, refineries, petrochemical plants, pipelines, and similar facilities, the potential for fire and explosion can still exist. The aptly chosen phrase, hazardous locations, refers to the areas where there is sufficient flammable material in the atmosphere that an explosion or fire could result if a source of ignition were available. While it is true that substantial experience and training are required to properly classify hazardous locations, the fundamental concepts are much less complicated than might initially be expected. The purpose of the common toggle switch is simply to make and break circuits. However, from time to time, the contacts of the switch will release a small arc when it is operated. The arc that is created is the release of energy that may have been retained in certain circuit elements. Motor circuits and other types of inductive loads typically store energy that is released as magnetic fields collapse when the circuit is opened. Typically, no problem would be encountered with the arc created since switches are designed to accommodate this relatively small release of energy. However, the question now becomes, what could occur if that same switch were located in a petroleum refinery? If sufficient flammable material were present in the atmosphere from the refining process to create an ignitable mixture, the toggle switch could become the source of ignition in causing an explosion, fire, loss of life, loss of property, and loss of production. Because electrical equipment can become a source of ignition in flammable atmospheres, the National Electrical Code includes articles that address the use of this equipment in these areas. Articles 500 through 503, the subject of this presentation, address traditional NEC approaches for treating these areas. Article 505 incorporates the use of additional concepts that reflect the interface with global standards. Starting with Article 500, the National Electrical Code provides definitions and classifications for designating hazardous locations along with detailed guidelines for the use of electrical equipment in those locations. Other publications, such as API 500 and API 505, produced by the American Petroleum Institute, build on the NEC framework to provide additional industry and application-specific guidance. The NEC attaches specific meanings to the language of classifications, and it is important to use those designations clearly and accurately. A reference to either hazardous locations or classified locations is appropriate. The underlying principles of hazardous locations are not terribly difficult to comprehend. Unfortunately, there are times that the discussion of this area of the code tends to make the fundamental concepts seem more complex than they are. In simplified terms, the fact is that there are only 3 types of hazards addressed by the National Electrical Code. The first hazard involves gas and vapor. It is logical to assume that if a flammable gas or vapor is present in the atmosphere, an explosion or fire could occur if a source of ignition were available. Gas typically refers to a material that is in a gaseous state at normal temperatures. A vapor, on the other hand, is produced by a liquid that evaporates to a gaseous state. While methane might be a good example of the gas, Ethanol and gasoline would be examples of liquids that evaporate to create flammable vapors. Typical locations that might, from time to time or even frequently, have gases and vapors present in the atmosphere in sufficient quantities to produce a flammable mixture could be a refinery or a petrochemical plant. However, it is important to recognize that it is not necessary for the facility to be a major industrial installation before hazardous locations can be encountered. Even small bulk loading facilities may create flammable atmospheres that must be treated with the same degree of care and protection as other, larger hazardous locations. While it may not immediately come to mind as a likely hazard, certain dust can also become the fuel for devastating explosions. In fact, OSHA, reinforced by a number of legislative initiatives, has undertaken a national program to emphasize the concern for explosion risk in the presence of combustible dusts. Therefore, the second type of hazard the NEC addresses relates to finely pulverized flammable dust in the atmosphere. Combustible dust may be suspended in the atmosphere in sufficient quantities such that an explosion could occur if a source of ignition were available. Typically, these might be areas that include dust from grains, spices, sugar, cocoa, and similar food products. The coal industry generates dusts of carbonaceous material that could be explosive when dispersed in the air. It is also true certain metal dusts, such as aluminum and magnesium, are highly explosive if suspended in the atmosphere as a dust. The third and final type of hazardous location, again recall there are only three, is designated as fibers and flyings. In these locations, the material is less likely to be suspended in the atmosphere and is not as finely divided. So, there is less concern about explosion. But this is still a hazard that might lead to combustion in the form of fire. Woodworking plants, textile mills, and other processing facilities that use materials of this nature could produce fibers and flyings. Since fibers and flyings would not ordinarily remain suspended in the atmosphere, they could settle on fixtures, enclosures, and other apparatus. If the operating temperature of the electrical equipment is high enough, or if the blanket of settling fibers and flyings cause sufficient overheating, combustion could occur. It is even possible that certain fibers and flyings that settle on top of heat-producing equipment could reach a point where they become subject to spontaneous combustion. In order to provide a more specific, consistent, and concise way to refer to each of the hazards that might be present in the atmosphere, the National Electrical Code has assigned a series of designations to the three types of hazardous locations. The hazard created by the presence of gas and vapor in the atmosphere has been designated Class 1. The hazardous locations resulting from combustible dusts are referred to as Class 2, and the presence of fibers and flyings has been named Class 3. These are the three principal categories that form the foundation for dealing with electrical equipment in hazardous locations. Once the type of hazard present in the atmosphere has been classified, it is important to next analyze when the hazard might occur. The distinctions to be made here are related to whether or not the hazard would be expected to be present during normal operations. In certain parts of a petroleum refinery or petrochemical plant, for instance, where normal operations of the facility could reasonably be capable of releasing hazardous material, it would be appropriate to expect a flammable atmosphere might be present. If routine maintenance procedures release hazardous material, or if repair activity that was performed on a frequent basis similarly released material into the atmosphere, it would also be appropriate and normal to expect the occurrence of an atmosphere that might create the potential for combustion. Therefore, this first set of circumstances is categorized as normal conditions. In contrast, if hazardous material was contained in a closed system or otherwise reliably prevented from building flammable concentrations in the atmosphere, then it would require a malfunction, failure, or catastrophic event for an explosive or flammable mixture to develop. Therefore, the presence of a flammable atmosphere under these circumstances would be referred to as abnormal conditions. The simplest example of a closed system that would ordinarily contain hazardous material, but might make the material available to the atmosphere if a failure occurred, would be sealed drums of hazardous liquid such as acetone. As long as the drums were sealed, no hazardous material would be expected to be in the atmosphere. However, if one of the drums was damaged during transportation or handling, vapors might enter the atmosphere. In addition, areas adjacent to those which contain hazards under normal conditions, to which the atmosphere could unexpectedly migrate, would also be included. Even though the hazard might be unlikely and unexpected, design considerations for electrical systems must still include that possibility. The National Electrical Code also provides more specific nomenclature for the conditions just described. Normal conditions are referred to by the National Electrical Code as Division 1. When hazards could develop during abnormal conditions, the code reference is Division 2. Although the categorical designations of normal conditions and abnormal conditions satisfy most needs to describe the occurrence of a hazard, there are a few exceptions that bump certain hazardous locations from a Division 2 designation to Division 1. The first of these are situations where a particular abnormal condition might create both a hazard and a simultaneous source of ignition. Since such situations would result in a higher probability of initiating an explosion, it is important to designate them as Division 1 even though they are abnormal. The second exception relates to metal dust. While it is certainly possible to confine metal dusts in such a way that they are not present in the atmosphere except under abnormal conditions, the fact that metal dust will also conduct electricity means that the potential for creating arcs and sparks in electrical equipment exists at the same time as the metal dust is present. It is best to treat these as Division 1 areas as well. The next and final set of considerations bearing on the classification of hazardous locations covers the nature of the hazardous material that is present in the atmosphere. The substances that will be found in Class 1 gas and vapor hazardous locations have been divided into groups based on their explosion pressure and flame propagation characteristics. These groups are designated A, B, C, and D. At one time, autoignition temperature was also included as part of the group designation, but as the science on the initiation of explosions matured, it became clear that this must be a separate consideration. It is critically important that the ignition temperature of each individual gas be evaluated when selecting heat-producing equipment to be used in those atmospheres. The NFPA, the National Fire Protection Association, produces excellent reference sources for information on the characteristics of hazardous materials, including ignition temperature. The first two groups, Group A and Group B, are generally the less frequently encountered materials found in industrial processing atmospheres. Group A contains acetylene, while Group B contains a larger grouping. Hydrogen is among the most common of the Group B gases to be encountered. Although a bit of a departure from NEC nomenclature, it is not unusual to hear of this being referred to as the hydrogen group rather than Group B. Consult the available resources from the NFPA and others for a more complete listing of hazardous materials in these groups. Group C and D contain most of the more common hazardous industrial gases and vapors. Since these create the bulk of the hazardous locations, it is not unusual to find electrical equipment designated for Group C and D only. The fact that hydrogen, Group B, produces higher explosion pressures and has different flame propagation characteristics from Group C and D materials creates the requirement for more robust equipment than that used for Group C and D only. Class 2 dusts are also placed in groups based on the characteristics of the material. These groups are designated as E, F, and G. While flammability is certainly an important consideration for segmenting the groups, electrical conductivity is also a factor in assigning material to its appropriate group designation. The final consideration relates to the dust blanketing effect that occurs after the material that has been suspended in the atmosphere begins to settle on electrical equipment. Heat-producing apparatus in particular must allow for the dust blanket that will likely impact the rate at which heat can be removed from the device. If unanticipated in the design, the resulting elevation in temperature could become a source of ignition. Group E, the first of the three groups in this class, contain highly conductive combustible material. As mentioned earlier, conductive metal dusts that are also explosive can settle on electrical contacts, creating the arcing and sparking that could then ignite the dust. Both a hazard and a source of ignition would occur simultaneously. Therefore, these highly conductive dusts must always be designated Division 1. Group F includes materials that tend to be related to fossil fuels, like coal and its derivatives. Through the years, there have been findings that some of these materials do have a limited amount of conductivity, but there is less concern that they will offer sufficient conductivity to create arcs and sparks that would be the case with metal dusts. Group G can be commonly thought of as grain dusts, since they make up a significant segment of this group. However, Group G also includes materials such as sugar, spices, and cocoa, along with the flour, starch, and other grain and grain products. Group B and Group F materials have temperature limits established for electrical equipment at 200 degrees C. Group G has the limitation set at 165 degrees C. While it is critically important to know the particular ignition temperature of Class 1 materials for precise selection of apparatus, it is less of a concern with Class 2 areas, since approved electrical equipment has been designed to account for the lowest combustion temperatures in each of the various groups. With the foundation of hazardous location nomenclature in place, it is now possible to consider some classification examples. Class 1, Division 2, Group D would be a typical classification that might be called out in an engineering specification. Analysis of the three designations in this classification provides information concerning the type of hazard, when the hazard might occur, and the nature of the hazardous material. The first step is recognizing that the type of hazard identified requires a Class 1 designation. The material in the atmosphere is either a gas or vapor. It has also been declared Division 2, which means that the hazard would not normally be expected to occur in sufficient quantities to create an ignitable mixture. Finally, the nature of the material has been determined to fit into Group D. It is a gas or vapor that shares explosion characteristics with materials such as methane, propane, and ethanol. In the second example, the location has been designated Class 2 Division 1 Group G. Analysis of the classification shows this to be a Class 2 hazardous dust environment where the dust hazard might be expected to be present as part of normal operations, Division 1. The material is one from the grain group, Group G, such as rice flour, corn dust, sugar, wheat, or similar material. While the NEC and common sense expect that only qualified practitioners are to be responsible for the classification, design, and installation of electrical systems for hazardous locations, it is still possible to encounter individuals who may not be fully familiar with the language of NEC classifications. It is important to listen not only to the classifications they provide, but also to the background discussion as well. It is not impossible to find some instances where the designations for class and division have been reversed in error. The National Electrical Code is the primary document intended for use in the application of electrical equipment in hazardous locations. There are also many other books and publications that have been developed to amplify what is available in the NEC. The NFPA has already been mentioned. Independent authors have also provided substantial texts on the subject. Other organizations, including the American Petroleum Institute, provide publications that emphasize and detail specific applications. Selecting some illustrations from the more detailed explanations provided in a number of these resources offers additional insight beyond the NEC for dealing with hazardous locations. In the case represented here, a source of heavier-than-air vapor is illustrated as being above grade in an outdoor and therefore well-ventilated area. This could be typical of a liquid petroleum fuel dispensing pump. Heavier-than-air vapors tend to settle toward the ground, and therefore the shape of the hazardous area reflects this type of vapor movement. This reinforces the fundamental logic behind the classification of hazardous locations that can be easily observed when presented in graphical form. Since a source is located outdoors, the natural ventilation of air movement could be expected to prevent the vapors from developing concentrations sufficient for combustion. However, if the air became unexpectedly still, or two trucks were positioned for refueling on either side of the pump, blocking ventilation, concentrations could grow to flammable levels. Even though unlikely, a risk of explosion would exist, and this location would be designated as Class 1, Division 2. It is interesting and important to note that a sump pump, manhole, or other below-grade chamber would revert to Division 1. Analyzing this further, it is already clear that this well-ventilated area would remove the hazard except in unusual circumstances. However, heavier-than-air vapors would tend to migrate and sink into depressions and below-grade chambers where they could remain. The assumption must then be made that regardless of whether or not hazardous material is currently present above grade, at one point in its history, the heavier-than-air vapor may have entered the below-grade area in concentrations sufficient to support combustion. Isolated from natural ventilation, it would be normal then to expect the hazard to be present, making it Division 1. In graphically evaluating a situation with lighter-than-air gas, a similar outdoor source would also have the area around it designated as Division 2. Since lighter-than-air gases dissipate on their own, it would be unlikely that sufficient quantities of the gas to create a flammable mixture would exist, so the risk of an explosion would be low. However, if a roof were to be built over the source, as might be the case for weather protection, that roof might tend to collect and trap lighter-than-air gases, forcing a more normal expectation that an explosive mixture could exist. This would create a Division 1 area above the source. It is apparent that the logic, although physically inverted, is similar to the previous analysis in which heavier-than-air vapor was trapped below grade. One of the important findings from conducting a site examination of this type is that the lighting fixtures selected for this application would be required to be Class 1, Division 1. The next consideration in dealing with hazardous locations is the potential for electrical apparatus to become a source of ignition. There are three circumstances in which these devices can become a source of ignition that might lead to an explosion or fire in a hazardous location. The first is arcs and sparks. Arcs and sparks typically involve gaseous conduction between opening contacts when energy stored in an inductive circuit is released as magnetic fields in the components collapse. In addition, the momentary, imperfect contact that occurs during any make-or-break function of a mechanical switching device could also release energy in the form of arcing and sparking. The second circumstance relates to high temperatures. Heat producers, such as electrical lamps, can reach temperatures that could initiate an explosion or fire in hazardous locations even during normal operation. It is quite clear that the routine functioning of electrical equipment could be the point at which an explosion or fire could ignite. The third circumstance, however, relates to failure of the equipment. Aging, mechanical fatigue, thermal cycling, and insulation stress can ultimately take their toll. Even a simple splice or termination of conductors could be subject to loosening after years of thermal expansion and contraction, vibration, and insulation degradation. But as in the first two instances, end of life for electrical equipment could lead to the release of sufficient energy for ignition in the form of arcs, sparks, and heat. With the understanding of how an explosion or fire could be initiated by an electrical source, it is now appropriate to consider how electrical equipment is designed and manufactured for these hazardous locations. In developing explosion-proof equipment for Class 1 Division 1 locations, much of the design criteria is based on the practical assumption that the flammable atmosphere and a source of ignition will come together. The issue then becomes a matter of controlling and managing the resulting explosion so that it does not propagate to the surrounding environment. The principles guiding the engineers involved in the design of these products are, first, to provide a separate or integral enclosure with sufficient strength to contain the explosion of the specified flammable material. Next, there must be certainty that the apparatus operates below the ignition temperature of the atmospheric hazard. And finally, a means must be provided to allow for the venting of the expanding products of combustion, but only after the flames have been quenched and they have been cooled below the ignition temperature of the surrounding atmosphere. To achieve the strength that will contain the explosion along with the defined safety factor, graphic analysis, mechanics calculations, and stress evaluations are employed to ensure that the enclosure has been properly engineered. The heavy wall construction is designed and manufactured to constrain an explosion while providing substantial safety margins. In addition to its essential strength, it must also be functional. The definition of heat-producing equipment in the NEC covers electrical devices that reach temperatures of 100 degrees Celsius or more. Heat-producing equipment must be marked with its operating temperature or a standardized T-code range. In the case of Class II equipment, where specific temperature limitations have already been determined, group suitabilities are the appropriate markings. This information is critically important to those with the responsibility for illuminating hazardous locations. The selection of lighting fixtures often hinges on the maximum operating temperature that must be evaluated against the ignition temperature of the gases, vapors, or other flammable material that could be present. Recalling the design assumptions discussed earlier that an explosion can occur within a Class I Division I enclosure, provisions must be made for the escape of the products of combustion, but only after they have been cooled sufficiently before exiting to a surrounding atmosphere that could also contain the hazardous material. Precisely engineered and machined flame paths are provided to assure that combustion is quenched before the burning gases reach the exterior of the enclosure. One frequently used type of flame path is the precision machined flange joint, in which tolerances are held to less than 15/10,000ths of an inch. This assures that the burning gases come in contact with a tightly controlled, broad metal surface before exiting the enclosure. The maximum allowed gap and the length of the flame path are a critical combination. It assures that there is sufficient heat transfer from the expanding exploded gases to the flame path to reduce the venting temperatures below the ignition point. In much the same way as flange-type flame paths function, threaded joints also use metal-to-metal contact to provide cooling. Burning gases that are expelled through these joints will travel over and around threads, losing their heat along the way. While Killark assures that the proper number of threads is in place for conduit openings and equipment using threaded covers, field technicians must be diligent with the threads that are machined on site for both hubs and conduit. Field requirements in the National Electrical Code state that a minimum of 5 full threads engagement are to be present in order to provide a flame path. All conduit threads must be tapped and tapered to NPT specifications. A standard NPT tapping die will provide the appropriate taper. Conduit must also be installed wrench tight to assure that no arcing or sparking will occur within the thread in the event that a ground fault occurs. The dynamic flame paths that are necessary for switch and push-button shafts are very similar to those found on machined flange flame paths. They are carefully machined surfaces with controlled gaps and lengths that provide enough metal contact for the burning gases to be cooled as they exit the enclosure. Having covered the basic concepts involved in designing and manufacturing equipment for Class I hazardous locations, it is time to return to the electrical toggle switch that appeared earlier as a potential source of ignition. The switch can now be placed in the specially designed enclosure that would be strong enough to contain an explosion if it occurred. It would be engineered to assure that operation is below the ignition temperature of the surrounding hazardous material. And finally, the enclosure would be manufactured to provide controlled flame paths so that any burning gases that might result from an internal explosion could vent only after the flames have been quenched. This is the solution to the Class I Division I challenge of providing a switch for these hazardous locations. Larger and considerably more complex enclosures for panel boards, motor starters, plugs and receptacles, and lighting fixtures are engineered and manufactured using the same conceptual foundation. These principles can also be adapted to smaller physical volumes. The employment of modern materials to create miniaturized explosion-containing chambers and flame paths around arcing elements have permitted the innovative creation of explosion-proof contact blocks. Compressing the technology to address the arcing elements also permits adapting alternative NEC regulations to provide an expanded range of enclosure options for many of the most common applications in hazardous locations. The assumptions governing the design of equipment for Class 2 locations are somewhat different from those for Class 1 locations. In Class 1 explosion-proof designs, it is understood that regardless of what reasonable steps are taken, it would be nearly impossible to consistently prevent gases and vapors from entering the enclosure. As one example, the natural expansion and contraction of air inside an enclosure as the electrical equipment goes through its normal thermal cycling could breathe in the surrounding atmosphere. In contrast, for Class 2 applications, it is possible to effectively seal out dusts so that no hazardous quantities of the material can enter the enclosure. Since a Class 2 enclosure can exclude dust, the likelihood that there will be an internal explosion has been removed from the design criteria. Enclosure walls no longer require the same thickness as in Class 1. The equipment is dust ignition proof. There are 3 key elements that must be carefully incorporated into the design of enclosures or integral housings for Class 2 applications. Gasketing material that has been proven to be resilient and non-reactive is among the approved methods for ensuring a dust-tight seal. Mechanical attachment is one of the most robust methods for assuring the permanence of gasket seating even as aging and chemical degradation take their toll. But there are now also a number of advanced adhesives and polymeric materials that provide the same reliability for Class 2 joint seals. Secondly, the equipment must be engineered to limit external operating temperatures so they do not exceed the 200 degrees Celsius maximum for groups E and F or 165 degrees for group G. Finally, additional analysis must be employed to account for the internal heat buildup and resulting temperature rise from a dust blanket that could occur if suspended material settles on the equipment. It is interesting that the nameplates for some Class 1 explosion-proof equipment also carry markings for Class 2. This is because the design and testing of the particular products also satisfy these requirements. One of the keys to achieving the dual ratings is that a closely toleranced ground flange flame path has such a small gap that it works just as well as an approved gasket in sealing out the dust. There are other types of flame paths that also work well. Dust blanket and operating temperature requirements are the same as for individually rated Class 2 equipment. However, it is critically important to recognize that it is never appropriate to assume that explosion-proof or other types of Class 1 equipment are automatically suitable for Class 2 dusts. The equipment nameplate must be marked for Class 2 and the approved group suitabilities. Equipment for Class 3 is primarily intended to minimize the entrance of fibers and flyings. In general, when approval is required, Class 2 equipment will be used where Class 3 is the designated hazardous location. The differences in approved equipment for Class 3 as compared to Class 2 are insufficient to warrant separate designs. National and specialized standards have been developed to assure that the design and construction of equipment for hazardous locations fulfill performance expectations. These standards are frequently associated with recognized third-party agencies and testing laboratories that thereafter provide listing, approval, or certification. In addition to Killark's own rigorous review and laboratory trial protocols, third-party testing and evaluation assures users that the equipment has been designed and manufactured in accordance with the applicable standards and has undergone thorough testing to assure that the performance complies with requirements. Among the agencies that are used for certification, approval, and listing of Killark products are Underwriters Laboratories, the Canadian Standards Association, and Factory Mutual. Several specialty agencies and a number of overseas listing authorities also review, test, and certify Killark product lines. Submittal to a third-party agency for certification is no simple or trivial matter. The typical procedure is quite complex and covers a broad spectrum of product construction and performance characteristics. The steps that are commonly part of the process include a full review of materials and construction, including drawings and prototype samples, even before testing protocols are contemplated. Once fabrication is found to be in compliance with the requirements, a battery of explosion and flame propagation trials will be conducted, followed by hydrostatic pressure testing. Heat-producing apparatus will be subjected to an array of thermal evaluations. A series of dust blanket experiments may also be required. Depending on the particular product, a string of environmental and vibration analyses would be conducted. Cycle testing, mechanical stress, and electrical endurance trials are also common. Aging and chemical degradation assessments are also required for certain materials. Again, this third-party examination process is in addition to the evaluations conducted in Killark's own engineering laboratory throughout the research, development, and proving programs. The explosion testing is conducted to assure that the enclosure is sufficiently strong to contain ignition of a specified Class 1 gas group and to prevent the propagation of flame to the surrounding atmosphere. It also provides critical experimental data for subsequent evaluations. The procedure involves filling the prototype enclosure with the specified flammable gas and then creating an artificial atmosphere around the enclosure that would also be ignitable. The artificial explosive atmosphere is held in place by construction of a 5-sided wooden chamber around the enclosure being tested. The chamber is then sealed with a thin plastic sheet as the 6th side. Once the enclosure and the surrounding chamber have been completely purged of free air with the specified flammable mix, the gas inside the enclosure under test will be ignited. The resulting pressure is then measured by a transducer, an electronic sensing device installed in the enclosure, and digitally recorded for the next stage of the analysis. Flame propagation is also evaluated, since any transmission of high-temperature products of combustion would ignite the surrounding atmosphere, causing the destruction of the plastic membrane that was used to seal the chamber. The gas and air mixture is varied throughout the testing series to discover the maximum pressure that can be generated inside the enclosure. Certain applications even call for lengths of conduit to be threaded into the enclosure to evaluate the added effect of pressure piling from a remote ignition point. Once the precise mixture that creates the maximum worst-case pressure is determined, several more shots are run to confirm the recorded information for the next test. At the conclusion of the explosion tests, the enclosure is then subjected to hydrostatic pressure testing. These trials involve pumping high-pressure water into the enclosure for a specified period of time to ensure the enclosure will withstand a calculated test pressure. The hydrostatic target value is derived by multiplying the maximum worst-case pressure determined during the explosion tests by a 4-time safety factor. For example, testing that recorded maximum explosion pressures of 130 psi for an enclosure would require a hydrostatic target of 520 psi. The enclosure would be connected to a high-pressure hydraulic pump and subjected to increasing water pressure until the target level is reached and maintained for the specified period. To meet requirements, the enclosure must sustain the target pressure without rupture or permanent distortion. Thermal performance is another essential evaluation that is undertaken on heat-producing equipment. In addition to the same explosion testing that is performed on other enclosures, the integral housings of Class 1 Division I lighting fixtures must be subjected to thermal testing to determine nameplate markings. The illumination of hazardous locations requires strict attention to the fixture's marked temperature ratings. It is vitally important that fixtures be selected with temperature markings that are below the ignition temperature of the hazardous material that may be present in the surrounding atmosphere of the application site. Whether it is the external temperatures that are required for Class 1 Division I applications or the internal hotspot temperature for Division II, the testing protocols are quite similar. Sample fixtures are prepared by affixing thermocouples to specific hotspot locations to determine operating temperatures for nameplate marking. Additional thermocouples are affixed to insulation and temperature-sensitive components to assure that the measured temperature rise is in line with the original design parameters. The fixtures are then placed in precisely controlled environmental test chambers where the ambient temperature can be held at consistent levels. As many as 30 to 40 thermocouples that had been used to prepare the fixture for test are connected to recording instrumentation through terminal boxes in the chamber. The final temperatures are recorded and certification reports prepared once steady-state temperatures are achieved. The nature of hazardous locations is such that other environmental conditions are commonly present that could be stressful to electrical components and interfere with their operation. Additional testing that assesses the enclosure's resistance to corrosion and the effects of rain, ice, and even high-pressure hose down are frequently included in a comprehensive evaluation and certification program. It is critically important to recall that the protection afforded by products for hazardous locations is dependent on strict adherence to the systems approach detailed in the NEC. Wiring methods, grounding, raceway options, and other elements must all be in line with the code requirements. A single weak link could undermine the integrity of the entire system. An essential system element that receives substantial treatment in the National Electrical Code is sealing. It is one of the principal mechanisms employed in explosion-proof protection to contain explosions that might be ignited by internal electrical components. The seal is critical in limiting the ability of an explosion to travel within the conduit system to another location. It will also help eliminate opportunities for hazardous material to migrate from one location to another. Sealing fittings are specifically designed to provide the means for creating the required hardened plugged-in conduit runs exiting from enclosures. Properly poured seals become a barrier to the explosive wavefront that would otherwise propagate through the system. The National Electrical Code specifies the requirements for placing seals in wiring systems for hazardous locations. It is important to consult the code for these details. As a general overview for Class 1, the NEC requires that seals be placed within 18 inches of explosion-proof enclosures that contain arcing devices. For applications without arcing devices that still require the use of explosion-proof junction boxes or explosion-proof fittings to house splices and taps, generally, no seal is required unless the conduit connection to the enclosure or fitting is 2 inches or larger. In those instances, where the conduit is 2 inches or larger, again, a sealing fitting must be provided within 18 inches of the fitting or enclosure. Exceptions exist in which a manufacturer may include an internal factory seal that eliminates the need for a separate externally poured seal. Or, perhaps a special rating may have been determined to require a seal be installed at less than 18 inches. In either event, it is essential to determine whether a manufacturer has provided additional sealing instructions or nameplate markings that apply to the specific equipment, device, enclosure, or fitting being supplied. These instructions and nameplate markings must be followed explicitly. Certain Class 2 situations also require the use of seals. However, in these applications, the purpose of the seal is to prevent the entry of dust into the dust ignition-proof enclosure from an enclosure that may not be required to be dust ignition-proof. The code indicates that no seal is required between two enclosures that are dust ignition-proof. Seals would be required, however, in the conduit run between an enclosure that is not required to be dust ignition-proof and one that is. The code also acknowledges that conduit geometry may be an effective means of preventing the transmission of dust from one enclosure to another if sufficient length is present. The rules and lengths depend on the direction of the conduit run. The National Electrical Code also addresses a number of additional situations requiring the use of seals, as well as detailing methods for treating multi-conductor cables and other wiring methods. Alternate wiring methods, such as cable installations, will typically require specially designed sealing fittings. These fittings are dedicated to meeting the specifications and installation requirements for both sealing and connections in these applications. It is very important to remember that the National Electrical Code is the resource on which to rely for sealing requirements. Pouring of basic seals is a straightforward process, yet it is frequently surrounded by confusion. Understanding the process in combination with a reasonable amount of practice are the keys to a properly poured seal. The components required for completing a proper seal involve the selection of a certified sealing fitting, the use of the recommended packing fiber, and the jointly approved sealing compound. Substitution of alternate material is inappropriate for a variety of technical, safety, and certification reasons. Once the sealing fitting is installed in the system in accordance with NEC requirements and wires have been pulled through the raceway, the process for pouring the seal can begin. Preparation of the seal now involves carefully reaching into the sealing fitting through the access port to separate the individual conductors so that an effective dam may be created with the packing fiber. The dam will hold the pourable sealing compound once it is mixed with water until it hardens. The thorough separation of conductors is essential to assuring a properly poured seal. Bunched, unseparated conductors could create spaces and channels through which hazardous material could migrate or an explosion could propagate. The code also has special rules on the treatment of multi-conductor cable when seals are required. It is important to repeat how prudently the conductors must be treated during the separation and damming process. The use of sharp implements to separate the wires and pack the dam must always be avoided. The risk of nicking or scraping the conductor insulation must be eliminated during this procedure. A thin, blunt cut, or rounded tip wooden dowel can serve well in assisting the separation and damming process and may be necessary with access ports available on smaller trade-size fittings. The sealing compound is next mixed with water in the proportions detailed in the provided instructions. After the compound is mixed according to the instructions, it can be introduced into the fitting in any convenient way that does not contaminate or otherwise change the mix. Continue filling the fitting until the compound reaches the bottom of the thread for the close-up plug to create a seal that complies with the depth provisions of the National Electrical Code. Once poured, the level of the compound must be verified after assuring that any air that may have been trapped has escaped. Wipe the thread clean to permit final installation and tightening of the close-up plug. The cleaning step will also assure that future inspections by the authority having jurisdiction will be simplified. The practice of classifying hazardous locations, selecting the appropriate apparatus and fittings, and undertaking installation and maintenance necessary to meet the stringent requirements of the National Electrical Code requires a hard-earned and effective combination of knowledge, experience, and judgment. Understanding the fundamentals of hazardous locations is a good place to start.